Okay, yeah. So, welcome everyone for the Origins talk today. And today we have Dr. Duo Xu visiting us from University of Virginia. Dr. Xu is now a Vico Origin postdoc fellow at Virginia, and he's mainly working on star formation in interstellar medium with the focus of using AI and machine learning. And Dr. Xu got his PhD from University of Texas at Austin, working with Stella Offner. Today, he's going to talk about AI4Astro. Yeah.
Thank you for the next introduction. And today, I will introduce our work using artificial intelligence, especially machine learning, to explore star formation and interstellar medium. And I want to advertise our website is the AI4Astro astronomy on GitHub. And we have published a series of papers using different machine learning techniques to explore a variety of tasks in star formation. So first, why do we care about star formation or interstellar medium? That's a basic question, because it's really important. It regulates the evolution of our galaxy. Starting with the atomic gas to the molecular gas, there's a chemical evolution or chemical transition. And then under gravity, magnetic fields, or star formation, will form different structures, such as filaments, and there are also feedback structures, such as outflows or bubbles. And then this feedback plus the death of stars, such as supernova, will return all this hot or ionized gas into the surrounding gas, such as the warm, neutral medium, or ionized medium. And this loop of ISM regulates or control the evolution of the entire galaxy, including elemental enrichment or the star formation processes. And why we need machine learning to study this? Because ISM data is really messy. We have tons of data, and it's big data, including archival data such as Spitzer, Herschel, that's all archival, and also ongoing ALMA, JWST, and the future SKA. That's tons of data, and they are really high dimensional, such as we have position velocity, including spectral information, which is difficult for us to identify structures with our human eye, because we need to rotate the cube and to examine into the detail. It's almost impossible to label this data by eye. That's why machine learning can help us. Then I want to highlight some of the work that human cannot do. That's learning some of the embedding information of the data, such as if you want to compare between simulation to observation, it's not that easy because we cannot exactly replicate the physical condition or chemical condition, but the machine can learn based on their embedding by learning a lot of the simulation or synthetic observation. They can learn some intrinsic or the embedding correlation between the simulation, the intrinsic physical quantity, to the observed data, such as the dust emission or molecular line emission. So machine can link these two really smartly, such as I will introduce some of the magnetic fields, infer prediction, or the radiation field prediction. And here I want a series of work we have done using machine learning or artificial intelligence, including identifying feedback structures, including bubbles and outflows, and also using traditional methods such as convolutional neural network. It's traditional for us, but it might be fancy to you. And we also introduce a novel, a state-of-the-art machine learning method, that's the Denoising diffusion probabilistic model, to infer some of the physical quantity, intrinsic quantity, based on observational data. So I will give a really brief review on the previous work I've done in the previous years, and I will give more focusing on this new technique, the Denoising model, to diffusion model, to some of the intrinsic physical quantity study. First, identify feedback structures. Why we need to identify them? Because it's important, it's everywhere. And feedback regulates star formation. And it can regulate the star formation efficiency and star formation rate really efficiently. Not efficiently, unefficiently, because they will suspend or suppress the formation of stars due to outflows or radiation bubbles or stellar wind bubbles. And also, stellar feedback will change the shape of IMF. If there is no feedback, we cannot reproduce what we observed of the IMF. There will be really top-heavy, will form really massive stars, but that's not in reality. With outflows, we will form more smaller mass stars, and they hit around 0.5 solar mass. And that's consistent with most of the observational data we have observed. And it's important, however, it's difficult to identify because it's in 3D. And also, it's really difficult for us to do a mask on pixel level of feedback. This is important because we want to quantify the mass or energy or momentum if we know exactly the position of feedback. But labeling this data is really time-consuming and also challenging for human. But that might be possible for machine because in machine learning, we're starting with the simulation. And simulation have the ground truth where the feedback is. We can trace the outflowing gas accurately. So here is what I developed in the past 5 years. That's the classic 3D based on the convolutional neural network. It's an autoencoder architecture. The encoder that will translate our observed image into features. So that's the embedded information. And the decoder will translate this feature into a new image, such as our mask and the positional feedback, or some intrinsic physical quantity, pixel level of the feedback. So this is widely used as well in medical imaging segmentation or in computer vision. To start with, as I mentioned, we're starting with the hydrodynamic simulation, which model outflow processes such as outflow plus radiation field, radiation feedback of driven bubbles. And we conduct radiation transfer to generate the synthetic data because we cannot actually compare or starting with the simulation because we cannot observe density or velocity. What we observe is the molecular line emission or dust emission. So we need to do radiation transfer to do an app-to-app comparison. We apply our machine learning model to actual observed data. In synthetic vision, we generate the synthetic 12CO and 13CO data cube. And then this tracer field is obtained from simulation because simulation, we know where the outflow is. We have the tracer particle. And this is our input. This is our target. We want to identify this outflow structure.
Can you say a little bit more about how you make the tracer image?
For the tracer, since in simulation, we can track exactly the position of each particle.
Sure, you have tracer particles, but there must be, it seems like there must be some
we will
choices made in how you define where you put your edge based on tracer particle velocity.
We set a threshold 2% of each cell that contributing from the mass from outflow above the 2% threshold. This threshold is detailed discussed in my advisor's paper, since we set different threshold. And 2% is the moderate choice where we can highlight the outflow low really clearly and without missing significant amount of entrained gas. Because outflow, they are not only coming from our stars, there are also entrained gas on the material that will also contribute to the kinematic, the dynamic kinematic energy or the momentum of the gas. So that also important. That's why there are detailed discuss on how we choose this 2% threshold or cutoff.
So is it always 2%?
Oh, sorry. In a cell, over 2% of the gas are directly coming from stars. Since the rest of the 90% or more, they are entrained gas because their velocity is significantly higher than the local velocity or turbulent velocity. And then we train our algorithm based on this training data. It's the input of the data cube, that's 12CO, 13CO, and then the target is the segmented outflow mask. And we test on observation data. This is an Perseus outflow, and the red is our machine identification, and the bluish is the 12CO emission, the total cloud emission.
Sorry, the red is the machine identification.
Yes.
What of
outflow.
Of the outflow. Okay, yes. Thank you.
This is PPV clear. So this is high velocity feature. Really clearly we can capture this feature. And we also identify these outflows and by plotting the red and blue contours on the entire Perseus data. And after we develop this method, I will give a quick review on our results. So we apply our machine learning to some nearby clouds, including Perseus, Rhesus, Orion, and Taurus, and we calculate the energy from outflows and calculate the dissipation rate of turbulence of this cloud. And we compare with the injection rate, the energy injection rate that's from the feedback, and dissipation, that's the turbulent dissipation, will decay across the time. And our finding is they can compensate. So that means currently turbulence can be maintained by the feedback energy. But if in terms of the total energy of feedback to the turbulent energy, it's not very sufficient, it's not comparable. It's only 10%, or for Perseus, it's much higher, but for the usual cloud, it's only 10% or even less.
And I'm sorry,
Yeah,
why are you
sure.
getting such a difference in your ratio between?
Yeah, that's a good
previous
point.
studies?
Yeah, that's a good point. Because for Perseus, I would say, especially for the turbulent energy estimation, because Perseus, they have a really large velocity gradient, since for the north part or the south part. These numbers are all adopted from previous studies. So I would assume there are some maybe caveats when estimating this turbulent energy without considering this large velocity gradients or the bulk motion. So that's why there might be some underestimation on the actual energy of the turbulent energy, because after subtracting this velocity gradient, the Perseus kinetic energy or the turbulent energy is not that high. So that might be a caveat.
Is this order more than order of magnitude?
Yeah, than the Rhesus. Yeah, but in
One
terms
of them, actually.
Yeah,
Yeah.
one of them.
yeah, but for the dissipation rate for this calculation, they are kind of comparable and also sufficient to maintain. Yeah,
For instance, the condition in Taurus and Orion is very different,
yeah,
and they're still order of magnitude different.
yeah, for the 3D energy. Yeah. Yeah, this is almost 1 of the magnitude difference for the feedback energy.
Yeah.
Yeah,
And sorry, just to,
Yeah.
so I'm clear, you're saying most of the difference with previous studies is in the denominator or in the numerator of the ratio?
both.
Okay.
Yeah, since for the previous work, there might be some missing outflow, but we identified by machine learning. And also our machine learning can extract or to tease out the contamination of the gas that are not coming from outflow, but caused by turbulent motion. That can also change our estimation or compared to the previous work. So there are two trade-off. One is the missing outflow, one is the contamination. Our machine can just tease these two compared to previous work. So there might be some difference between our work and the previous work.
Okay, but you're suggesting your work is more accurate than in.
Based on our machine learning method, we would say yes.
So can I say,
Yeah.
so how do you deal with like overfitting when you're doing these
Uh,
trainings?
that-
Because yeah.
That's a good point. I will show later for my test for the test on the new simulation or other stuff. But I haven't included in this part, but I will introduce
Okay,
later.
yeah,
That's a lot of, that's definitely
Right.
the overfitting issue is always the case for machine learning, definitely.
But there's probably value in comparing among the different clouds, right? I mean, since you're applying a uniform method, maybe the difference between Ophiuchus and Perseus is
that's good. Yeah.
interesting.
Exactly, that's a good point, because we are always trained on one type of distribution or one type of data. When we apply to the new data, there is always caveats because their data distribution is always different. So that's why we need to evaluate or validate the performance or the validation of the machine learning model, whether they are doing good on their unseen data or out of distributed data. I will address that point later in my talk. Yeah, and also from our estimate, after we have the prediction of outflows or bubbles, we can identify the actual energy injection rate or injection scale based on studying the power spectrum, spatial power spectrum of the outflow mass and compared to the total integrated intensity. And what we find is there is a typical half per second injection scale for the outflow. That might be consistent with the outflow width or length to the typical outflow in torus. And we have similar findings for this typical break power law for outflow region. So that might indicate some injection scale for outflows. And also we have a comprehensive data set or comprehensive sample. We also do some statistical study to compare the outflow orientation versus the B field. This is a large scale B field direction from Planck. So what we thought is this large scale B field is not necessarily correlate with the outflow orientation because outflow is really local. And when they formed, they are on a dense scale that's roughly sub-parsec scale, even smaller on the core scale. For large scale B field direction, this from Planck, that's on the order of parsecond or even larger. But what we find is there seems to be some alignment rather than random. And our study is consistent with the previous work. We are using JCMT, that's kind of smaller scale magnetic fields on core scale. And their magnetic fields also similar to what we find. So peaking around 30 degrees with a misalignment, but generally it's not random. It's more towards align rather than misalign. Then I will introduce our work using the same machine learning model architecture to predict the direction of B field. The base idea for this work is B field can regulate the morphology of gas. This can be found in atomic gas, such as H1, or the molecular gas in CO. Since they have filaments or fibers, their orientation is consistent with the either dust inferred polarization angle or the starlight inferred polarization angle. That's the B field direction. So they give us some inspiration. We might use this morphology information to predict the B field direction based on molecular line emission data. And this is an even larger survey from Planck. So what they find is there is high alignment between the structure orientation with the local gradient with the B field on the low density region. So that means the structure is aligned with B field in low column density. However, they will flip. The B field will be perpendicular to the structure at dense region. So that's similar to some filamentary structure or other because of gravity. Because gravity will concentrate onto filaments and then it will drag the B field to perpendicular rather than alignment. And also, this can be found in some simulation work because B field regulates the velocity of the gas. So that make their velocity dispersion to be larger, aligned with the B field rather than perpendicular. So from our PVQ, we can use this information to predict the B field. So similarly, we train our data with turbulent cloud simulation. So that includes different alpha Mach number, such as the sub-alpha and trans-alpha. They are all relatively strong B field. And we then validate on some simulation, a new simulation, apart from this code. We run on Orion, that's the proto-based simulation code, and we test on Enzo and other simulation. And what I want to highlight is our machine learning model is able to predict this direction really good compared to some of the traditional VGT that's using the gradients of morphology. Simply just calculate gradients on each pixel. So that can be affected by the local fluctuation. It's not that good, but our model is able to predict the B field's direction on a high precision, I would say. And for the trans-alpha, so that means the turbulent is a little bit stronger than the sub-alpha. And our model is still okay, but with some scatter compared to the traditional method. That's the velocity gradient, the local gradient. And what I want to show is we apply our model to the entire torus cloud. This is the Planck observation, the CO emission, and we overlay with the Planck inferred dust polarization angle using streamline. And this is Planck observation of the polarization angle or B field angle. This is our machine learning model prediction. If we calculate the angle dispersion or angle difference, what we can see is in most regions, they are consistent, but in some dense region, they are not because gravity. Gravity can significantly change the morphology of gas. So that's consistent with our intuition. So our model only validates on the purely turbulent cloud without significant presence of gravity, because that's the starting point or the basic assumption from our model or the simulation. And what I want to highlight here is, it seems our machine learning model might be a better tracer to trace the actual B field direction compared to Planck, because in Planck, they might be affected by the foreground dust that are not actually coming from the CO emission region, because there is a systematic, what we found is a systematically offset between our prediction and the Planck one. And our angle is more consistent with the morphology of the gas rather than Planck. So this Planck angle is coming from both the CO emission region, and also there are some foreground where there's no CO, but there might be some dust, cause this systematic offset. So this is a kind of the validation or some, I would say, demonstrate our validation or the fancy of our work. We are able to predict the actual 3D or to disentangle the foreground contamination of the B field angle prediction rather than Planck. That's the overview of my previous work using the convolutional neural network. And then I will focus on the new machine learning model. That's the state-of-the-art ones, the DDPM. So what is DDPM? That's the diffusion probabilistic model. That is a really SOTA deep learning model. And it's based on the Markov chain or Markov chain. And it models the random walk in the data space. And also, it has really rigid mathematical improvement or the mathematical formulation. So it's really easy for us to interpret it and also trace how the data is transforming from distribution to another distribution. And I want to highlight that compared to the convolutional neural network, DDPM is really easy to train without any fine-tuning or to modify a lot on the data architecture, on the algorithm architecture. And for the DDPM, they have perfect alignment with our physics because they are inspired by the thermodynamics of diffusion process. And in astronomy, we have a lot of the random walk and diffusion processes, such as the photon or the turbulence. They are all random or quasi-random processes contributing to the actual data distribution. Especially for the radio transfer, the photon is perfectly aligned with our DDPM inspiration. That's why we use DDPM in our following task. Here is kind of the framework of how DDPM actually work. If we are going from right to the left, that is the diffusion process. So this is, for example, this is what we want, such as the number density or the volume density of the molecular cloud we want to recover. And for the diffusion process, that is step by step adding noise to this image until it's purely Gaussian. And for this Gaussian, so we can draw, since Gaussian is easy to draw, so that's why for computer science region or computer science community, they always starting with a Gaussian and to recover this data distribution to the actual what we want, our target distribution. This diffusion process is well mathematically modeled. However, how we recover from noise data to the clean data, such as step-by-step, that is challenging. We use machine learning to train how to denoise from a noisy data to cleaner data based on conditions. This is the input, such as the column density. So in this work, we are starting with the column density map to infer the actual gas density. Since density is a really key quantity what we interested, such as it matters with the free fall time scale and also matters with the estimation of star formation efficiency, star formation rate. And for some of the work, such as magnetic fields estimation, we need density. because DCF requires density in the denominator. And density also matters with some of the estimation on the chemical reaction stuff. There are some methods to estimate the actual density of the cloud. For example, there are some density tracers, HC3N. So we can use the excitation condition for different transition line of HC3N to determine the actual density, give us some range on whether it's dense or it's diffused based on their excitation states. Or there's another simple method, just assume some typical length of the molecular cloud, such as it's a spherical or it's a cylinder. All these methods, this one is difficult, but that might be accurate. But this one is just by simply assumption. It's not valid, I would say. So that's why we are using DDPM machine learning to predict the volume density. Here, the volume density we're using is the line of sight mass weighted volume density. It's into two-dimensional. We are not actually reconstructing actual three-dimensional data because it's almost impossible to starting with a 2D column density to the actual 3D data. And that's why we're starting with the mass weighted volume density. So the simulation we use, they include different kinematics, different magnetic fields, and different evolution stage. So they have collision cloud, or they have the isolated cloud, or they have different E fields.
Sorry, I don't quite understand what a mass weighted volume density is.
Yeah, so we will have higher weight on the dense region, but less weight on the diffuse region. Since we are really care about
Density weighted.
density weighted.
Density weighted.
Yeah.
Yeah, so you're not assuming some scale getting
No.
a mass, okay.
No, just density weighted. Yeah,
So you're just
density.
doing like
Density is
row, integral row,
integral
row.
rho square.
Yeah, okay.
Integral of rho square divided by rho. Exactly. Yes. Since
Is that equivalent to you have like multi-molecular lines and you model their excitation and which gives you a volume density? Is that equivalent to what you're finding here?
For this work, I will show our prediction is highly consistent with the other method, but we are not actually using the molecular line data. We are starting with more simple one. It's the column density map. It's two-dimensional, and also it's really easy to obtain from either spacer excitation map or the Planck continuum dust emission. It's everywhere. And I just want to highlight, there are some traditional methods, such as using column density to do a power law conversion to the number density. And there are significant scatter. Here, I just show there are for different B fields and for the different kinematic, the non-collision or collision. And I will show how that works later using the power law conversion compared to our method. To give a quick view on how we train that model. So this is a random noise. This is Gaussian distribution. And this is our input. That's the column density. This is just integral on the other side by density. And we denoise step by step. In total, we have 1,000 steps, but I just highlight several key steps here. And we will recover the actual density, the number density, volume density.
I'm sorry, there is a question, I think, from Yancy. He raises his hand.
Oh, yeah.
Yeah, sorry, just a quick question. I'm still missing something. I think Kaylin was hitting on this, but maybe I just didn't understand. You seem to have a single volume density associated with a column density, but there's really gradients in reality along the line of sight. So there's something I'm missing here. I apologize. Maybe you could clarify.
Yeah, that's a good point, because what we are modeling actually, that is, we're only focusing on the dense region. So that's why we are doing the mass weighted or the volume weighted. And there might be different, and also, yes, that's why we are including different training sets. We have different kinematics, so there will be different structures on our side. But what we want to really highlight is where the density part we can trace. So that means, for example, if we have a plan of sky column density map, what we really care about is this core, actually, what is the similar number density in this core? We are not using the highest density, but rather than the lines of sight mass weighted, because this number is within, I would say, with some test within a factor of 2 difference between the actual really dense core density compared to the actual mass weighted, since rho squared integral over rho, that number is almost consistent. And our integral is more mathematical, I would say, reasonable compared to just picking the highest density. And this density represents the typical dense region density.
Maybe, so the condition is just the integrated column density
Just rho,
calculation.
yeah.
T0 and ground truth, do those have the same units, or is T0?
Same units.
But the ground truth is a ground truth, that's not a volume density, that is a density weighted column density.
Not density weighted, this is density weighted density. Since it's density square integral.
Okay, so the left panel, so you input column density,
Yeah,
but you're training for density weighted density.
machine does not care the unit.
Right, I
Yeah.
understand, yeah,
Yeah.
I understand the machine
Yeah.
doesn't care, I just want to make sure I understand what
Yeah.
T0 is versus ground truth. So,
Yeah,
okay,
yeah, this is in unit of per centimeter cube.
right.
This
And
is
so-
per centimeter square.
And T0, you're also, but you're,
This is 10 centimeter cube,
yeah, exactly, okay, I got
centimeter
it.
cube. This is all centimeter cube.
Right.
This is condition. Condition means it's not directly starting with this point. They are the embedding information for machine to use. That's the ancillary data. That's the conditional data. And here is the performance of our machine learning model, the DDPM. And also we use the CASI2D, that's the convolutional neural network. If we use the power law fit on this correlation between column density and number density, and we would say their error, this is the error distribution in PDF, is okay to some sense. I would say factor of 3 difference or factor of 10. But our machine learning DDPM is peaking here. So they have a really small or tiny dispersion. And for visual comparison, this is the column density map. This is the actual mass weighted or density weighted density, the number density. And for the power law conversion, we are always missing some dynamic range because for some region, there might be high density, but their column density is not high because there are some associated structures here. Machine can capture this really great, but power law conversion cannot. Since machine can learn not only the actual number in each pixel, they are learning the actual two-dimensional structure. So there are at least we know the 2-point correlation or even multiple points correlation on this structure to infer the actual value in that region. So that's the powerful part of machine learning compared to simple 1-to-1 conversion using power law or other traditional approach. We also test our model on some of the observational data. This is the torus column density map. And this is our number density prediction. Especially, there are some previous work using HC3N to infer the number density. And our result is identical, I would say. Less than a factor of 2 prediction on this number, 10⁴ centimeter cube. So we will say these filaments is actually filaments. They are not sheet or projection issue. It's an actual cylindrical structure. And also I want to highlight here. So we compare the actual column density distribution and the mass weighted density distribution. For the low density part, they look similar, but there will be significant difference at high density. So for some of the high column density, they are not go as linear as the number density. So in a really dense region, their column density might not that high, but there will be significant difference for the number density.
Sorry, you were sure by the estimation of the density, you know that's actually a cylinder instead of a sheet. Is because you know the density, they divided the column density.
Yeah, we know the length.
Scale, okay.
Yes, we know the length. And that is comparable. That's 0.2 or 0.3 per second for this filament's length. And that is similar to the width of the filaments. And that's the question that's always people ask, how do I perform on the unseen data or all of distributed data? Since we train on a cloud prediction and that's run by Enzo, we test on a new simulation that's run by Orion or proto-based data cube. And it's different physical condition and initial condition. It's a turbulent box, no gravity, and it's isothermal. There's no heat and cooling. And we test on some different magnetic fields, strength. For the distribution of the column density versus density, this gray shade, they have significant difference here, the distribution here. But our machine learning model, here's the diffusion model performance. That's still centering perfectly here compared to other traditional methods. So that's give us some confidence. DDPM for machine learning part, they can really good at to predict something on the unseen or out of distributed data, even if we train on some limited sample. That's the powerful part of DDPM. Although there are dispersion here, if you want to overcome this part, what we need to do is to increase our training set by implementing more data sets, such as different physical condition or different B fields or initial condition in our training, and we can cover a wider range of our data. So similarly, we use DDPM to predict radiation field. So radiation field is really common component, or really important component in ISM, because they have providing radiation pressure and also they have radiation feedback. But measure this radiation field is a little bit challenging because we need to base on some assumptions, such as we need to assume from dust by integral over the entire infrared luminosity from thermal emission, or we use some tracer such as C+ or O1 line to infer the interstellar field, but that will be expensive because identify these lines need to go to space. So that's why we're starting using machine learning to use dust emission, multi-band dust emission to infer the actual irradiation field. The simulation we use is StarForge. I would say the StarForge simulation is also the cutting edge one because it includes almost everything: the gravity, magnetic fields, and heating, cooling, thermodynamics, and also all kinds of feedback, supernova, outflow, and stellar wind-driven bubbles, and radiation. So it's a particle-based. So they can down to the resolution of 10 AU. Although there are only several particles on the order of 10 AU, they cannot actually fully resolve the disk. So that's why when we do synthetic observation, we use two types of star spectral when we do the radio transfer to generate the synthetic dust emission. One is Planck, one is YSO spectral that's from Robitaille's model, which includes the disk of the YSO. So that's the two assumption ends on the stellar spectrum. And to make that more efficient, we just clustering the stars into 4 categories: the hot star or cooler star. And we adopt 2 different dust models in our simulation, in our synthetic observation. For this region, we'll start deep grains. That's from K17 paper. And for the diffuse region, that's below 10 to 6 centimeter cube, we use the astrodust that's from Drain's model, which captures some of the PAH emission, but not fully. So here are some examples of our synthetic 4.5 plus 24 and 250 micron. That's Spitzer plus Herschel emission. And this is a radiation field from simulation. In simulation, we can trace actual radiation field. This is also line of sight emission-weighted radiation field. So for some of these star-forming region, the radiation is really high. And this is the more noisy region where there are multiple stars that are illuminating the gas. And this gives you a sense on how our training data cover the observational processes of observational physical conditions. So the red one is our synthetic SEDs for different evolutionary stage and for different condition, because we have StarForge, they model a series of, or we explore a lot of the physical conditions, and we adopt some of that, but not fully. And this blue dots are the observational data from Spitzer and Herschel on Monarch 2. This is also a star forming region in our Milky Way. And I would say our synthetic data can roughly cover the widespread of this actual observed data. So we are trying our best to make sure our synthetic data is similar to the observed data. Otherwise, the model might not do a good job because there are two different distribution data. The machine learning model might fail because two distinct distribution. And I want to just give some caveats. In our dust model, we didn't include H2 emission or really sophisticated pH emission. So that's why when we choose which band we want to do the prediction, we only use 4.5, which are less affected by H2 emission, contamination, or pH emission, and 24, and also 250. And the reason why we do not include the 350 or 500, they are similar because they are on a power law. That's just based on the dust emissivity. They have a similar power law. They just trace the column density of the gas. Yeah.
So should we make anything of the fact that most of your synthetic SEDs at around 10 microns sort of clustered to south of the blue data points?
Yeah.
I mean, it looks like they're more inconsistent with the data in that region of wavelength space.
Yeah, this is from different YSO models. So, and also I want to say here, that is caused by the pH emission. This is 8 micron. We can see there are some spikes here. So in our dust model, we model part of the pH that's from astrodust, but the pH emission is not only coming from thermal dust emission. There are some other excitation mechanisms, such as shocks or others. They are not actually well modeled in simulation or synthetic observation. So that's the caveats why in observation, we have really high 8 micron emission, but in our synthetic model, most of the 8 micron emission is down here. It's almost lower by factor of here. So that's the caveats why we do not include 8 micron in our prediction of the radiation field, because we cannot model really well. That's why we just choose 4.5 micron.
If you have like a strong dust feature in a certain wavelength range, you don't use it, for instance. SEDs could also, observed SEDs. It has
a lot of features.
YSOs, there's especially like a silicate feature or some strong features in certain wavelength, you just don't use it.
We didn't because we are not well modeled. That's the part of that. Since our current dust model, they are thermal dust and they have different composition. But for certain wavelengths, they are not that good. Although, for example, here, there are 10 or 12 micron, there are also some spike caused by silicate feature. That's part of modeled well, but for 8 micron, it's not that good. We are underestimating because the excitations were different from the thermal to the pH emission, because pH can be excited by other ones, such as the fluorescence and also the shock.
So you didn't include fluorescent light or?
No, they are not well modeled here. That's why. That's the caveats, definitely.
For the stellar YSO model, so each YSO in the simulation is a particle in there, right?
Yeah.
It includes so it's just is it like a sink or is it like one star? Does it include like multiple stars?
Multiple stars. We have in some snapshot, we have 100 stars in one image. And that's why we're just clustering the stars into 4 different categories and using a star field to do the retracing rather than do individual stars. That would be too expensive. Since RADAM 3D can do a star field rather than individual stars.
But in the simulation, each
star is a sink.
Particle
is a sink.
Oh, okay.
It's identified. They are sink particle.
But in reality,
is resolved. And here are some performance on our dust emission plus the prediction. And I would say they are doing really good job to predict actual radiation field where they are really high radiated region or where the luminous star highlighting the ISM. And to be more quantitatively, I have plot this one. This is a ground truth radiation field versus the predicted radiation field. And I convert it into a more traditional quantity, that's the G naught. That's much easier for us to quantify. And we cover really wide range of G naught from traditional 1 G naught all the way up to 10 to 5. And this is our test set. They are from the same sequence of simulation and using exactly the same dust model. For here, we use the same simulation, but we use different dust model when we do the radio transfer. Here we use both the purely big grain and purely diffused grain, that's the astro dust, or small grains. And they are still doing good on the simulation, although there are some scatter. They are in different dust model. This is kind of unseen data, I would say. And I will also show more unseen data. This is a totally new simulation with never including our training set, but they have an initial radiation field 100 times higher than the initial setup. So that will yield different structure and different ground truth because their value will be systematically higher than our training ones. And our prediction still lies on this one-to-one line with some offset. And here are some implication of underestimation because in our training set, we never including this high ISFR, the radiation field. So that's the reason why we cannot recover or underestimate this part. But on average, we are able to retrieve the relative radiation field on a really precise order, although there are some suspected offsets. But if we only care about relative intensity in a molecular cloud, we can tell where is strong radiation, where is really weak radiation. Also, this is another test. This is also using a really new, different treatment on the heat and cooling. Since StarForge or Gizmo Code is always updating their treatment on their physics. So that will yield different output. And also, this is using different initial condition. This uses turbulent driving for 2 crossing time and let it decay and undergo gravity, gravitational collapse. And our prediction also kind of one-to-one line, but there are significant scatter here. And for the prediction, still roughly okay to predict where there is high radiation region, where there is faint radiation region. Roughly okay, but not perfect. But I would say this is unseen data. In the simulation, never know. And also, especially different physics in the simulation. That's the caveats why it might perform not that good compared to the other ones. So that's why our future work can do is just include different treatments of this radiation field or the physical condition to enhance the actual diversity of our training set. This is our test on the actual observation data. This is the Spitzer plus Herschel 4.5, 24, and 250 micron emission of 1 or 2. And our prediction of the radiation field, that is highly consistent where there is really active star-forming region. So this gives us confidence that machine is doing some reasonable job compared to the other method. And also, radiation is not actually associated with 24 micron, which we assume since 24 is warm dust, they might trace some of the radiation field, but that's not the case. Since we did some statistical study, there is no significant correlation between 24 micron emission versus radiation field strength. So
which one is better best then?
That's a good point. What we find is there are more correlation on the 250, but still not as strong. Since for each single band, there are no really good correlation between this radiation field versus their emission. 4.5, there is an issue because there are foreground stars or background stars. And 24, what we thought it should be the best.
If you use H alpha, what is it?
That's a good point. We don't have the data. We haven't trained that, and we are not modeling that. That's a good point. So that's why we want to enhance our machine learning methods to broader spectrum, such as from optical bands all the way to radio bands.
UV, and radio and
radio.
shorter wavelength.
Yeah.
So actually, UV field, then there's you could use UV
Yeah.
For the radiation field, it's more sensitive there, for instance.
Yeah, definitely. So that's why we need to retrain our data with new training sets. And that's the question also, which physical quantity can infer some of the radiation field? Can dust temperature do that? The answer is no. This is all inside data, so we know the ground truth. And this is the formulation from previous work that's using dust to infer the radiation field. Because we assume where the radiation field is strong, the dust will be heated, so their temperature will be higher. But what we see is very significantly underestimating on this radiation field because there are extinction on the lung side. So it's not good. And this is on R2. This is our predicted radiation field, and this is that temperature derived by multi-bands dust emission. And they're consistent, so dust temperature seems to be not a good candidate for us to infer this radiation field. So our estimation might be a new metric, a new quantity can help astronomers to study the condition of molecular cloud or star forming region. Then that's a new topic using diffusion model to identify structures. Here, let's show the expert here. So that's the CMR filaments, the collision-induced magnetic reconnection filaments, which is formed by the flipped or reversed magnetic fields cloud colliding. So this kind of configuration might be really common in reality because in Orion, so Orion A, we see this flipped B field by Zeeman and also by Faraday rotation. So this initial condition is common, and that's why this type of filaments might be common in our universe. So what we want to do is using machine learning to identify these candidates to study the forming mechanism of filaments. So Shuo has done a lot of the simulation work on the physical parameters exploration using different B fields and different common density or radius of the cloud, and to comprehensively model the colliding of two clouds with reverse B field forming filaments. And what I did is to use this synthetic dust emission of filaments combining with some turbulent structure, because this type of filaments is really easy to see by our human eye. It's easy to extract. But when we put that into our turbulent cloud, is that still easy to identify? So that will be much similar or comparable to the actual observed data. So that's what we want to do. Use this image as a training set to train the model to identify this filamentary structure based on this messy dust emission with noise and also turbulent structures. Here are some performance. We use two different machine learning methods. One is the CASI2D, that's the convolutional neural network. One is diffusion model. And here is the dust emission, and this is the ground truth where we can label the actual position of filaments. And our model is doing good. Besides, we also generate some artificial filaments that just stick, or some stick with some wiggle. So that's the fake filaments. CASI2D, so that's a convolutional neural network, can distinguish these fake ones, but diffusion model cannot. So that's the caveat. So since diffusion model might have some false detection, but for the CASI2D here, they are missing some of them, such as the fake filaments. So if you want to have a really comprehensive candidate of the filaments, we need to combine both methods. So that can give us some high confident candidates of filaments. So this is the ROC curve as the receiver operating characteristic curve. That is plot the correlation between false detection versus the true detection. So that simply means this: if we recover 80% of the filaments in a data set, we might introduce roughly 2% or 3% of the false pixels that's being misclassified as filaments, the CMR filaments. This is for CASI2D, and for DDPM similar. We might be able to recover 70% of the filaments pixel with roughly 5% of the false detection. So that's why it's really important to combine both methods to do a more comprehensive analysis on our target. We do not trust either of them, but combining them give us really high confidence that have a similar morphology, at least morphology, to the actual filaments of CMR. To evaluate our model validation or the performance, we test on the wholly new simulation. This is the HD simulation, no magnetic fields. So there's no CMR filaments. But our model seems to misclassify some of that. But by combining both prediction, there are still some false detection, I would say. By looking at their morphology, I would say that might be indistinguishable to the actual CMR filaments, to this filament. So that's why machine can just fail, because we cannot differentiate these two filaments, such as the fake filaments here, to the CMR filaments. By human, then machine cannot do that either. So that's the caveats here. But I also want to highlight some previous developed fail finder algorithm identify filaments. We just identify all types of fibers. So any type of short ribs, just identify as filaments. So I don't think it's a good approach for us to actually identify elongated filamentary structure. So we can extend our model to not only CMR filaments, we can identify typical filamentary structures with more cleaner outputs compared to the other method. So that's our future work we can try. We then test our machine learning model to torus filaments. This is B213, and this is Orion A. And by combining these two predictions, I would say for this filamentary structure, they have a similar morphology in terms of morphology, because machine learning are always based on morphology of the data or the image, similar to the actual CMR filaments.
So,
Yeah.
when you say combining, are you just talking about visually comparing, or do you have a process of like,
Actually,
iteratively combining?
Yeah, for the prediction,
quantitatively?
for the combine of the data, we have the cutoff. Since we have the receiver curve, so we can choose different threshold for which positive or false detection rate we want to reduce, such as we can set a 5% of the false detection, and we know the threshold. For this threshold, we apply to the output image. Since this image is the just prediction of the value, what is the probability of this pixel to be filaments? And we just set this threshold and just doing the simple logic and to combine this one plus the DDPM prediction, we can get more comprehensive prediction. We combined both are predicting this as a filament.
But you're effectively weighting them equally, the two methods in that case?
Yeah. We didn't give them specific weight for either model. Yeah, we treat them equally because both have caveats. So that's why we do not trust either of them, but combining them, we would say might be a better approach.
It seems like you have information buried in there somewhere about where, under what conditions, one model works better than the other.
Yeah, that's true. Yeah. From our test, machine learning, especially for CNN, they will fail if there are some really bright blobs happening, because CNN is not as stable when they treat some of the unseen data. They are not very well doing on the normalization of the image. But DDPM, they are doing really good on this unseen data, but they have some misclassification. Since they identify all this kind of stick, since we did some tests, stick-like structure, fake filaments to be actual filaments. So that's the caveat. So that's why we need to combine both to make sure there are no, the CNN, they are not affected by the bright region, and also the DDPM, they are not misclassifying the fake structure to be semi-filaments.
So right now, this is only based on morphology to
morphology.
estimation. In principle, we can include like a velocity information, like we train using the PPV cube.
Yeah.
But that's very, very challenging.
Yeah, PPV, since machine learning, especially for DDPM, they are really computing consumption. So they require almost 100 cards to train. Especially this data is 512 image. images, 512Q images. And it takes for me almost 2 weeks for the training. So that's why it's really slow. But for training a smaller image, such as 64, it's only 1 day or 2 days, should be okay. So there are some trade-offs, whether we want to do high resolution data, or we can just do a chorus data first to get some results, and then we can do more backend analysis on this data. And this is Orion A, and this filament is identified by Shure, and we successfully identified this part.
Where in Orion A is that? Like hard to find.
L6041.
Oh, yeah, okay.
Yeah, so it's kind of the demonstrate our validation or the performance of our machine learning model. Then there are some preliminary results using DDPM and machine learning to predict the B field strength. This is as preliminary results. So since there is a really natural correlation, that's the Quadrant's law. There is density versus B field strength. There is a kind of power law. So that's why it inspires us whether we can use column density, for example, which is easy to obtain to predict the magnetic field strength. Since magnetic field strength is easy to measure, we need to make certain assumptions, either using Z-man that's expensive and also that's only 1D, or using DCF, that's the Chandrasekhar Fermi, that's based on some morphology of C, and then we use just DDPM plus to predict the B fields based on morphology and the column density map. Seems performs pretty okay or better than the just simple conversion of Quadrant's law. This is still preliminary results, and we are thinking about including some dust emission in the future.
Need to remind you that time is over 1. Yeah.
Oh, sorry. Yeah, this is the last slide. And we're also using DDPM to generate simulation. So this is what the preliminary results using DDPM to generate the turbulent patterns. Since running series of turbulent stuff might be time consuming, but generating this one is only in seconds. This can be a negative training set for us to study the morphology of gas. So just give you some sense on how machine learning can help us to accelerate the generation of simulation in the future. So I want to stop here, and the big idea is machine learning is revolutionizing our astronomy community, and we have tons of work we can use machine learning to help us to explore, and especially they have great potential for a variety of tasks in the future. And I will stop here. Thank you. Sorry for the time.
Okay, first Yancy raise hand, and then we'll ask you a question.
Yeah, just one more on the density predictions you got. And you actually have a picture of it here in your finishing slide of the torus central filaments. You might connect with Samantha Shabelli, who's also there at Virginia as a Jansky Fellow.
Yeah.
3D dust radiative transfer models, which are predicting the density profiles that match a whole suite of continuum observations. And so, again, it's curious of like, what is that picking out? Even the HC3N that you quoted, that's a very nice paper, but it's only picking out one density along that line. And there's issues that we've been running into in our research group where we use multiple molecular lines to try to predict the column density or abundances. And when you run through RADEX, for instance, doing rate of transfer is only a single zone model with a single density, single temperature. But obviously, when you have different transitions with different critical densities, they're actually probing at different densities and maybe different temperatures within your source. So no single zone model actually fully captures the true non-LTE. You have to go to a real model in 3D space. But I'm just kind of curious if you could do some kind of comparison like that and see what you're actually picking out along line of sight.
Yeah, that's a good point. Yeah. Actually, I talked to Samantha a while ago, and she told me we are interested to compare with what she did compared to our observation. And for the line of sight structure, that's also really challenging for our simulation modeling, because we are also modeling the one cloud. We didn't consider in the actually line of sight. There are multiple clouds or different components. That might be a challenging part. Yeah. So that's why I'm thinking about in the future, we can start not using column density, but rather we can implement more velocity information, such as we can use the field data as well as the complementary data set to train our model to capture this velocity as well, to get a more comprehensive infer or prediction on the density at several points of the cloud, since we might disentangle the actual structure of the cloud by implementing a variety of data sets, including velocity stuff.
Thank you.
Thank you.
Any other question? If you don't, the tour is here this week, so please sign up and go to this, find this, available time. Otherwise, let's end here and let's thank to. Okay.